Assalamualaikum. Hi all. So we move to the last part of the chapter 2, which is the application of the partial derivative. So this we have another two applications, which are absolute extrema, and also the last one is Lagrange multiplier. So this one is a continuation from local extrema or relative extrema. So we move to the absolute extrema. So if you have seen in the local extrema, what you have done before is you have to find the critical point, okay, by finding the partial derivative with respect to x and y, and you have to equate by 0 to solve for the critical points, and then you have to apply the second derivative test, and using the specific condition here, you can justify whether you have a local max or local mean and also saddle point. Okay, so that one is for the local area. We don't give a specific region. Okay, so this just like unbounded region, because we don't have, if you look at the example that we have seen in the video, we don't put the specific region for the local extrema. Alright, so now we want to extend the knowledge by finding the critical point to find out the absolute extrema. Absolute mean the max, the highest one. If you say that local maximum, so that what is the value of f for the particular point x and y that give you the highest value. And then if you have an absolute minimum, which is the most minimum one. But for the local, we don't bother whether that one is the most max or the most min. Okay, so for this part, so the way of the method is more tedious than the local extrema. You have to do a lot of think, which is your step is longer than local extrema, because for the local extrema or the relative extrema, you just find the critical point and then apply the second derivative test, and you can justify, okay, you determine whether it is max, min or saddle. But for absolute, you have more step, okay, because we want to find the max one and the min one. Okay, okay, so for absolute extrema, there are two types of situation. The first one, we consider it is a bounded region, so we give a specific region. You imagine that you have a surface, and you know that the surface is very, very large, and then we give instruction that we just want to find out the absolute extrema on the specific region. So we call that as a bounded region. And then the other case is we don't specify the specific region, so we just want to find the max and the min. That one is just like a local extrema. Okay. Okay, so the idea is, imagine that you have a surface. Okay, so last time when we have a local extrema, we don't specify the specific region, so we just use partial derivative to help us to determine the maximum value and the minimum value, and also if there is a saddle point, then we can know at which point that we have that situation. Okay, but for absolute extrema, imagine that you have this one. Okay, this is a very large surface. So we gave a limitation, which is a bounded region only at this triangle shape, or if you this one is on the region on xy plane. You can see the triangle shape here. But if you match that triangle with the surface, so we just want to find out the absolute max or min in this area only, which is bounded. Okay. Similarly, we have this one. We have another surface maybe. So you can see that we limit region only at this triangle, which is on the surface. We're only interested to know which one will give you the highest one and the smallest one. So maybe from the figure here, you can see this one. This one will give you the highest value of f here z. Okay, we have a different function here. So the z is the value of f here. That is the highest, and maybe this one is the lowest. Okay, but we do not know because this is a 3D. So we can, if you try to plot this in the GeoGebra 3D, so you can just play around with the graph. But this one is fixed, so we don't really know. That's why we have to use the partial derivative to help us to determine the exact value. Okay. So these are the steps. So you can see that the first two steps, I think, the same as we obtained for the local extrema. Before this, we find the partial derivative with respect to x and y, and then we equate that by 0, and then we solve that simultaneously to get the critical point. And then, so that is the first two, just like the local extrema. And from here, for local extrema, so you have to apply the second derivative test. But for the absolute, we don't have that step. So you can see the step 3. So you have to evaluate or compute the values of the function f of z at the critical point that you obtain in the step 2. And also you have to determine the boundary. The point lies on the boundary line of the region. Okay, and then you have to list all the boundary points along the line of the region and also the critical point, and you have to evaluate them and you have to compare, and then just find out which one is the highest one and which one is the smallest one. So for the highest one, we call that absolute maximum, and for the smallest one, we call that as the absolute minimum. That's it. So you can see here, no need second derivative test if it is bounded. So closed and bounded. Remember I mentioned just now, there are two cases, closed and bounded region, and the other one is open region. So for this one, for this type, is applicable for closed and bounded region.